In this video, we are starting our section on line integrals of scalar functions and their applications. Our goals are to compute the mass of a wire, to define what a line integral is when I'm dealing with what's called a scalar function, and how do we compute them, how do we determine the arc length of a curve using these line integrals. Then we'll talk about how we calculate the center of mass of a wire, and finally how we calculate the average value of a function along a curve. So in this video, we are going to review how we calculate the mass of a straight wire. Okay, so I want to first look at the case where the wire has uniform density. So I want to look at an example which says find the mass of a straight wire that is 5 centimeters long with a uniform density of 12 grams per centimeter. So what does this mean? I'm going to draw a picture. So imagine that we have this wire, this straight wire. So imagine we have this straight wire, and I'll draw like the end of the wire, and it tells me that it's 5 centimeters long. So the whole thing is 5 centimeters long. So uniform density means all the way through the wire, the density stays the same. It is constant the whole way through. It is evenly distributed. So the fact that it tells me that it's 12 grams per centimeter means, I'm going to give myself a little bit more space here, that if I were to split this up into 1 centimeter long blocks, this 1 centimeter has a mass of 12 grams. If I did another 1 centimeter cut out, that would have a mass of 12 grams, and so on. So if I wanted to calculate the total mass, it turns out that what you do is you multiply the density times the length. Density times the length. Because, this has a mass of 12, this has a mass of 12, and so on. We're going to have 5 of these pieces that each have a mass of 12. So I got to multiply 12 times 5. And if I check this with units, density is 12 grams per centimeter. That is multiplying the length, which is 5 centimeters. So the centimeters on top here cancel the centimeters on bottom, and that leaves me with 60 grams, which is what I'd expect. If I just add 12 plus 12 plus 12 5 times, I get 60. Okay, so the units for density are typically mass on top per unit of volume. I'm going to fill in the blank, volume on the bottom. But you might have noticed that in this problem, on the bottom, it wasn't a unit of volume, it was a unit of length. And that's okay if I have a wire or rod like this that has a constant cross-sectional area. So when I slice it into pieces, the area of one of these cross-sections stays constant the whole way through. And if that's the case, I can write the units of density as being mass per unit of length instead, which is what we saw here. Okay, so now let's talk about the more interesting case, which is what if we have a non-uniform density? So let's say that there's a straight wire that lies along the x-axis from the point when x is A to where x is B, and that the wire's density is given by this function rho of x. So this symbol that kind of looks like a P but slightly slanted, this is the Greek letter rho. So that represents my density function. And the units are mass on top and then units of length on the bottom. My goal is to find the mass of the wire. So let's begin by drawing a picture. So I'm going to draw the x-axis because the problem tells me the wire is on the x-axis. So my x-axis, it tells me the wire is in between the points when x is A and when x is B. On that portion of the x-axis, that is where the wire is. So it is in between those 2 points. All right. But the problem tells me now the density is not staying the same the whole way through. So there might be one part of this wire that's lighter, and then at different points, that weight gets distributed differently. So maybe on the other end, it's heavier. So what I'm going to do is let's first chop up this wire into pieces. So I'm going to cut it into pieces. So I'm cutting it. And don't worry about drawing the exact same number of cuts that I have. Just make sure you have several of them. It's for the purposes of the picture. And let's write that down. I'm chopping up the wire. I'm going to chop it up into n pieces of length. I'm going to say the length of each of them is delta x. So the length of this first one is delta x. The length of that second one is delta x. And so on. Every single piece here has length delta x. Okay. So what I'm now going to try to do is approximate the mass of each of those pieces. So let me focus on this first piece. I'm going to call that mass m1. And what is that approximately equal to? Well, I know mass is density times, in this case, it's going to be density times the length of that piece. So to get the density, because the density is changing, I'm going to pick some test value in that interval. So maybe somewhere here. It doesn't really matter where I pick it. And I'm going to call that test value x1. And what I'm going to do is I'm going to plug this test value into my density function. All right, so that is going to be rho, and I'm plugging in x1. So even though the density changes throughout that interval, I'm going to assume that it actually stays the same throughout. And that's why this is going to be just an approximation. So I'm going to take that density, multiply it by the length, which we said was delta x. All right. So what I'm now going to do is take the masses of each of these pieces, which I'm going to approximate in the same sort of way. So I'll take test values within each region. So maybe in the next region, the test value is somewhere on the left, and I'll call that x2. Maybe the next region is right in the middle, and I'll call that x3, and so on. So in this way, I can say that, the mass of piece number I is going to be approximately equal to, take the density, plug in your test value, I'm calling it x sub I, and multiply it by the length of that piece, delta x. All right, from there, let's sum up the masses of each piece. So I'm going to call that total sum I'm going to call the total mass capital M, capital M. And M, the actual mass, is going to be approximately equal to each of these approximations I was getting added up. So that is M1 for the first piece, M2 for the second piece, M3 for the third piece, plus ... I'm saying I'm splitting it into n pieces, so the last one is going to be M subscript n. Okay, so if I sum up these pieces' masses that I have, their approximations, I'm getting this. So far, this is just an approximation. If I want to make this exact, I need to now take a limit. I need to take a limit as the number of pieces, n, approaches infinity. If I take an infinite number of pieces, then this approximation becomes exact. Another way to write this, instead of saying n goes to infinity, is I could also say, all right, i.e., I can also say, in other words, that delta x, the length of each of these pieces, that is approaching 0. So now let's put this together. The total mass, if I want to get the total mass, what we did was we're going to sum up, and remember my notation for sum, this is going back to calculus part 2, is we use the sigma notation. We're summing up these masses, which are given by rho of x sub I times delta x. And what does I go from? So the first value of I is 1. That's giving me this first piece. And it's going up until n for that nth piece. Okay, so that is giving me this approximation for the total mass. To make it exact, we have to take the limit as the number of pieces approaches infinity. So this is what's called a Riemann sum. A Riemann sum is defining this total mass for us. But one of the big things that we would have learned, again, back in calculus part 2 is this limit of Riemann sums can be rewritten as an integral. An integral that goes from a to b, the starting and ending points of my interval. And then what happens is this function, you write that same function, except the xi changes to an x, and the delta x changes to a dx. And I have my integral. So I'm defining this total mass using this Riemann sum that ends up being this integral. And the way I evaluate that integral is the fundamental theorem of calculus. Fundamental theorem of calculus. Which just basically says, now I can do the antiderivative of this function, plug in these limits of integration, and subtract like I'm used to. So let's end this video. Let me highlight this formula. My formula for total mass, I'm just going to highlight the integral portion because that's the part that we're going to be actually evaluating. Let's end the video now by doing an example. Okay, so this example says, now use that formula to find the mass of a rod of length 10 centimeters that has this density function. And this is the density at a distance of x centimeters from the left end. So let me go ahead and get it started together by just drawing a picture. So I have this, tells me I have this rod. I'm going to draw the endpoints of the rod of length 10 centimeters. And it says that x represents how many centimeters we are from this left end. So right at that left endpoint, that must be when x is 0. We're distance 0 away from that left end. So the right endpoint has to be 10 if the whole distance is 10. From there, I want to try to set up an expression for mass and evaluate it. So I want to have you try this as a warm-up. So pause the video for about 4 minutes to try this. So pause it in 3, 2, 1, try it. Okay, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it. So using our formula from the previous page, this mass is going to be an integral from 0 to 10 of my density function. For me, that is x times e to the negative x squared. And then I got to put a dx next to it. And now I got to do this antiderivative. Okay, and this I can handle with a u sub. I'm going to let u be equal to this exponent, negative x squared, because then du, its derivative is, I'll get negative 2x, but then I have to write that dx next to it. The reason I know that it's going to work at this point is du, that derivative was negative 2x. But I see that same function in the integral just off by this constant multiple, this factor of negative 2. I see the function x in the integral here, multiplying my other part. That's an indicator that this u sub will work. So now I can take this and let's isolate the dx. So I'll divide and get du divided by negative 2x equals dx. So I can sub in. So when I sub into this, I have x times e to the u, and then the dx part became du over negative 2x. Okay, so nice. The other thing that I have to do is, when we have these limits of integration, and I'm doing a u sub, I have to convert them. Because right now these are in terms of the variable x, but I'm switching to the variable u, so I got to convert them. So right now it's x equals 0 and x equals 10. Let's plug those into the u sub. So if I do that, if I plug 0 in for x, u equals 0. And if I plug 10 in for the x, u equals negative 100. So the 0 became 0 and the 10 became negative 100. All right, so now from here, I can simplify this. The x's cancel. There's that negative 2, this constant, that I can factor out to the front. So I'll get negative 1/2 in front. Integral 0 to negative 100. The x's cancel, and I'll get e to the u, du. So from here, I could do the antiderivative right now. One slight simplification I'm going to make, which is optional, is sometimes, I notice that the number on top is smaller than the number on bottom, and I just stylistically like it better if the number on top is bigger. So I can switch the order of the integral and put the negative 100 at the bottom and 0 at the top. And what that does is it switches the sign of the whole thing. So I'll get positive 1/2. Positive 1/2 when I switch it. E to the u du. And again, if you didn't want to do that, you don't have to. There's just a stylistic preference. Okay, you'll get the same thing either way. So now I can do my antiderivative. So that 1/2 in front stays there. And then the antiderivative of e to the u is just e to the u. And then I got to plug in my negative 100 and the 0. So the 1/2 is just factored out. I can just leave that factored out. And now I plug in my limits of integration. So if I plug in 0, e to the 0 is just 1. And then minus, plug in negative 100, I get e to the negative 100. And that should be my mass. I just need the units. And for mass in this problem, those units were grams. And we have it. There we have it. So in the next video, we will take a look at how we can generalize this and find the mass of a curved wire in space.